In this video, I'll help you understand the basics of skeletal tissue. When we talk about skeletal tissue, we're really talking about bone tissue and all of the things that are attached to it, including ligaments and tendons, as well as the bone marrow within the bone that gives rise to new blood cells and platelets. So here are the overview of the overall functions of the skeletal system: support, protection, movement. Movement here isn't actually done by the bone, it's done by the muscles that pull on the bone, but obviously you have to have bones in order for the muscles to have something to pull on. Storage, look at this, calcium and phosphorus in particular are stored within the bone, as well as some magnesium. These are very important minerals that are used by the nervous system, the muscular system, the immune system. And so over the years, life has evolved a way of storing these important minerals when there's an abundance of it in the diet, and then releasing these minerals slowly over time to keep the blood or extracellular fluid levels where they need to be. Components of the skeletal system include bone, cartilage, and tendons, which attach muscle to bone, and ligaments, which attach one bone to its neighbors and hold the joint in a normal relationship. Cartilage, as a part of the skeletal system, we can look and see how it's built and the cells that are involved. Anytime you see chondro, you should think cartilage. So blasts are immature cells that are developing or creating the matrix. Remember this term from our histology chapter? The matrix is the non-living material within the tissue. And the matrix is always made by the blast cells, chondroblasts in the form of cartilage, osteoblasts in the form of bone. Once these chondroblasts have completely surrounded themselves by cartilaginous matrix, they go into retirement and maintenance mode. They still have the capability of maintaining the matrix around themselves, but they don't really move around because they're sort of trapped. It's kind of goofy, but imagine a bricklayer working on a closet and then he bricks himself in, so he's stuck. This is sort of the situation of the chondrocytes. They live in the little cavity, the closet, the lacuna, so plural is lacunae. Cartilaginous matrix is primarily a stiff jelly called proteoglycan matrix, and then there are sparse collagen fibers interwoven to give it a little resiliency. Perichondrium is the connective tissue surrounding the cartilage. It's made of collagen primarily, and that's a connective tissue. That's what this stands for right there. The articular cartilage is typically hyaline cartilage histologically, and the word articular here really means to form a joint. So look at your knuckles, bend and straighten your fingers, and you can see where the knuckle bends. There's a little bit of an enlargement there, and if you could see inside, you'd see something that looks a bit like chicken gristle, a rubbery, stiff material that prevents the bones from rubbing against each other. And because it's rubbery and slippery, it allows me to bend and straighten my joints without hardly any friction at all. Bony matrix contains different materials, a little proteoglycans, but it's mostly calcium and collagen. The calcium, in the form of these calcium phosphate crystals, we call hydroxyapatite. And because it doesn't contain carbon, this is said to be the inorganic part. Collagen, being a protein which has lots of carbon in it, is the organic part. And the proteoglycans are sort of like really stiff finger jello, right? Almost rubbery, but a little flexible and a little elastic. So our bone contains a slightly bendable part and a really stiff and stony part, and because they're put together, it's the best of both worlds. If it were this image is upside down, so funny, got it from the publisher that way, by the way. This says, without collagen, if we didn't have the rebar, if we didn't have the flexible string inside, our bones would be far too brittle. If we didn't have the calcium, our bones would be very rubbery and they wouldn't hold us up or protect our brain. So we really need to have both. I think of construction here. If you've ever stood on a bridge when a heavy truck drives over, you know the whole bridge flexes and bounces a little bit. It is stiff enough because of the cement that the truck can drive across, but it's flexible enough that it doesn't just crumble underneath the weight. This is exactly the same situation that we see within our own bone. The collagen is the rebar, and the hydroxyapatite is the concrete. Using very much the same terms that we talked about in cartilage, bone cells are osteoblasts. They create the new bony matrix through a process called ossification, and eventually they completely entomb themselves, like the bricklayer making a closet and bricking himself in. We see here a living bone cell called an osteocyte, but it can't really move around. It's totally sealed in within its matrix, unlike an osteoblast, which does move around and make a lot of matrix. The osteocytes are stuck in the lacuna, and their job is just to sort of maintain the bony matrix in the immediate vicinity. It does so by getting nutrients and secreting its waste and products through these tiny canals, which sort of interconnect this whole network of retirees, right? They're retired osteoblasts called osteocytes. Now, these are the most interesting of all. Osteoclasts, they're like the Zamboni machine. It's going to come around and scrape up the edges of the bone and any bone that has broken down, or in the event that the body needs more calcium or phosphorus released, osteoclasts dissolve bone. We call this resorption. And it does it by sort of going around like a little Zamboni machine, right? This is the ice making machine at the hockey game or at the ice arena. The osteoclast moves along the surface of the bone and then uses little secretory vesicles of acid to dissolve away a thin layer of bone, thereby releasing the calcium and phosphorus for metabolism. In the case of a fractured bone or an infected bone, these guys might need to come in and do a lot of work, but most of the time we think of the osteoclast activity being more or less balanced with the osteoblast activity so that our bone is sort of continually maintained and turned over. Here we see that the osteoblasts can make the bone in a couple of different ways. The woven bone is sort of a temporary phase that we see during fetal development and during fracture repair. Over time, the woven bone is remodeled into what we call lamellar bone. A lamella is a layer, and we see that this makes a nice solid little layer of bone, and then depending on if we make it in a loop or in a little wiggle, it's going to show us this, either compact bone, where the layers are very dense and there's hardly any space between them, or in spongy bone in the interior, where the layers form these little plates called trabeculae. Let me come back to that in just a few minutes. Okay, so when we look at a long bone like this femur, we see on the surface, and really on the surface of all of our bones, is this very hard, durable stuff called compact bone. Because it's on the cortex, the bark, the outer layer, we can call compact bone cortical bone. Notice that it ends, though, it's not all the way through. Our bones aren't solid, compact bone, or we'd probably weigh 20, maybe 30 pounds more than we weigh. Instead, there is spongy bone on the inside. The spongy bone, or trabecular bone, gives spaces for us to store bone marrow. It's very delicate tissue that creates new red and white blood cells and new platelets. These spaces in the spongy bone also allow us to store fat in the form of yellow marrow. So, bone has a surface layer called compact or cortical bone and an interior called spongy bone. You see here on this cranial bone, the orientation is the same way, right? We wouldn't want the spongy bone on the surface, or we would get dented or bruised much more easily. We want the surface to be durable, and the interior can afford to be spongy. When we look at a compact bone under a microscope, what we see is this, little rings like the rings of a tree. At the center of every ring, there is a blood vessel, arteries and veins, and oftentimes nerves as well. This serves like a tiny well, a tiny spring, and the first bone cells to move to town, they want to be as close as they can to the nutrient source. But the second and third and fourth waves of new immigrants who come to this tiny village end up living quite a distance away from the nutrient source. And so there are these tiny canals that allow nutrients to get out like spokes of a wheel coming out from this central canal. If we skip ahead just a couple, we can see this diagram shows us all of the structures we need to know regarding that little village. The village is called a Haversian system, or an osteon. The villagers are the Osteoclasts who live in their little houses called lacunae. The rows of houses, the rings of the tree, if you will, are the lamellae. The central canal contains the arteries and veins, and the tiny canals, canaliculi, connect one osteoclast to its neighbors, and so ultimately to the nutrient source. In this way, bone can be maintained for many, many years. Each of these osteoclasts maintains a small part of this osteon, and collectively, the whole collection of osteoclasts keeps this one osteon very hard and durable. Now, in cases where there may be damage to the blood vessels supplying this bone, we would see a little region of bone that dies. It's called avascular necrosis. And depending on where the bone is or how much of the bone is damaged, it could lead to a pathological fracture. Very simple. Long bones are long, flat bones are flat, short bones are about as wide as they are tall, and anything else we call irregular bones. When we look at the structure of a long bone, whether it's this femur or even one of the small long bones in your fingers, the phalanges, we use this vocabulary to talk about the different parts. The shaft is the diaphysis. The ends are the epiphysis. So this head of the femur is the proximal epiphysis, and then down the diaphysis at the end of the femur, we would see the distal epiphysis. The epiphyseal plate is the growth plate, which is actually cartilage, allowing new bone to invade and slowly elongate the neck of this femur. So too the shaft. All of our bones grow, and that's how we get taller, until we reach skeletal maturity, where this epiphyseal plate will close up, and then we leave just a remnant of compact bone that goes right through the neck. That's called the epiphyseal line. So it's a very subtle difference, but the plate is cartilage, and that means you could still grow taller. Once you're done growing, then it seals up with bone, and it's now the epiphyseal line. In the center of any long bone, but especially these large ones like the humerus and the femur, we see very large medullary cavity. This word medulla means the center. So the medullary cavity means the central opening. And this is filled with bone marrow, red marrow as children, and then gradually fills in with yellow marrow for fat storage as adults. Although obviously we still have some red marrow to provide for new blood cells throughout life. It's usually found in the flat bones and no longer in the limbs like we see in children. Here's another perspective of a long bone looking down the medullary cavity. We see the diaphysis, the shaft, and we can see that this bone is wrapped in collagen called the periosteum, and then we have a layer of compact bone or cortical bone, and then in the center, spongy or trabecular bone. The endosteum, by the way, is similar to the periosteum, and it lines all of the internal cavities, including the central canals of all of these osteons and all of the medullary space and space between the trabeculae. In the next video, we'll be learning about bone development.